SwayamPrabha. Digital India. Educated India.
Hello and welcome to this lecture on manipulator mechanisms design. So in the last couple of classes we have looked at, we started off with kinematics, then inverse kinematics, then we looked at dynamics, trajectory planning, control systems, linear control, nonlinear control. Then we are now looking at mechanisms design or manipulator mechanisms design that basically tells us what are the important things we have to keep in mind when we are designing a robotic system. So we look at some of the basic important things that we have to keep in mind, and also if you're going to buy a robot, then which kind of robot are you going to buy? So these are things that I addressed in today's lecture. So today we'll be looking at manipulator mechanisms design, and the first thing that would come to your mind is when you're talking about a robotic system, either to design a robotic system. So we are going to design, if you're going to design, or you're going to buy a robotic system. So for the cases of design or purchase of a robotic system, okay, you're going to design or you're going to buy a robotic system, the first thing that comes to your mind is the degrees of freedom. So we have seen that if you want to do a particular task, what is the minimum degrees of freedom required? For example, we have a table here and we have an object which is kept on the table. I want to pick it up and I want to place it here. Okay, how many degrees of freedom are required? Now that would depend on the object and the task. Okay, for example, for this object, because it's a symmetric object, it's a cylinder, you'll be requiring 3 degrees of freedom. What are the 3 degrees of freedom? My x, y, and z are here, and the x, y, z axis. So you are required to position the object on this table, which means you need x and y, okay, which are going to define the location of the CG of the object, let's say on the table where it is touching the table, and then z direction to move it up and move it down, okay, to take it up like that and then put it here. So that is upward z and downward z. So that is 3 degrees of freedom. Okay. Now to catch this object is a symmetrical object. That means it's a cylinder. So from the top you see it's a circle. So you can catch it if you have a 2-finger gripper. We can catch it in any orientation. We can catch it like this, or we can catch it like this. So in this particular case, position is 3. Okay, and orientation is not required. Now the rotation orientation that we say may not be required for this. Okay, so we can orientation is not required. Why? Because it's a symmetric object. But on the other hand, so 3 degrees of freedom, okay, for symmetric object. But if you look at if the object we picked up was not symmetric, for example, this is another case, okay, where we have a rectangular object. Okay, so we have a rectangular object which is kept. Now, if you want to pick this up and keep it here, now you'll require 4 degrees of freedom. So you'll require x, y, z, x, y of the object plus z for putting it up and down, and you'll also need theta for orientation of the gripper. This is something we had discussed in the second lecture, right at the beginning, that depending on the task, you have to define your degrees of freedom. Now it also depends on the shape of the object. So in this particular case, we have our x, y, and z, and we have the orientation. So this object from the top would look like this. So either you catch it like this, or you catch it like that, which means you need an orientation about this axis. Okay, this axis or this axis, right? A rotation there. So that would mean 4 degrees of freedom. So for a symmetric object, 3 degrees of freedom. In general, 4 degrees of freedom is the minimum degrees of freedom required. So the first question when you're going to buy a robot or design a robot is how many degrees of freedom, and we can define it this way. Now most industrial robots have 6 degrees of freedom. Okay, now 6 degrees of freedom correspond to what? They correspond to 6 degrees of freedom of the object. Okay, so for an object, you know, it can translate in 3 directions, it can rotate it about 3 axes. So it's 6 degrees of freedom. But most tasks in industries are limited to welding, okay, spot welding mainly, spray painting, okay, then pick and place, And for these applications, normally 5 degrees of freedom is enough. Now, for example, if you're doing a spray painting, suppose this is a spray painting gun and the robot is holding it here. Okay, this is just an example. So we have a robotic gripper which is holding this, and we have a spray gun here from which the spray is coming out. Okay, so this would require that you should orient the spray gun in such a way, position and orient, but you do not require the rotation axis here. Okay, so you don't require that the spray gun to be rotated about its own axis. So which means that you do not require 6 degrees of freedom. This is an application where you require 5 degrees of freedom. Similarly, if you think in the case of welding, okay, so when we are welding, if you look at the welding, the way welding is done, this is a surface on which we are welding, and this is my welding electrode, and there's this is the welding arc, and the robot is holding the welding gun. Okay, so this is my robot who is holding the welding gun. Now, as we are welding, we need position orientation of the electrode, plus we may need some angle like this or like that, but we do not need a rotation about this axis again. There is no point in rotating the electrode about its own axis. So what this says is that essentially you require 5 degrees of freedom again. You do not need 6 there. So in many industrial robots, you'll find that it is 5 degrees of freedom because of the task that it is required to do. Okay. Now, if the task involves, so we have seen that depending on the task, we define the degrees of freedom now. Now, again, depending on the task, if there are constraints that the task is going to impose. So, for example, task with constraints. Okay, for example, the robot has to get inside a very narrow passage like this and pick up an object from here. So we have an object there, and the robot now, which is here, is going to get inside there and is going to pick this object up. Okay, like that. Now, what is going to happen is, because there is a constraint, so what it means is that although this robot has 1, 2, 3, 4, 5 degrees of freedom, 5 or 6 degrees of freedom, or you can see that it has 1, 2, 3, 4 links, the moment it gets inside this narrow passage, it is constrained there. Similarly, it is constrained there. So what this constraint will do, what the constraint does, it takes away degrees of freedom. So if the robot has 6 degrees of freedom, and the moment it gets inside there, what will happen? Some degrees of freedom will be taken away because it can't move, it's stuck now. So in that case, you will need to put more degrees of freedom. Okay, so if for a case of a task with constraints, you may require greater than 6 degrees of freedom robots. Okay, so 6 DOF robots may be required for constraint tasks, and such robots are very often called redundant robots. Now, redundant robots can be in terms of the number of joints. Okay, it could be redundant, okay, or it could also be because of the task. Okay, for example, in the previous case, when we are picking up an object, in this particular case, if I'm picking up an object and I'm putting it here, okay, in this particular case, this particular application, okay, and I'm using a 6 degree of freedom robot, this job could be done with 3 degrees of freedom. So in this particular case, with respect to the task, it is a redundant system. Okay, so please note that this redundant is either the robot has more than 6 degrees of freedom, okay, or for doing a task, it has more degrees of freedom than required. Now, if it has more than 6 degrees of freedom, like in this case, okay, and it is doing a task in here, then also it need not be redundant. So please keep this in mind, because it is losing degrees of freedom when it is doing the task. So you should carefully look at the number of links it has, the number of degrees it has, and the task, how many degrees of freedom it is losing, before you can decide whether it's a redundant robot or it's not a redundant robot. So the first thing we saw is the degrees of freedom. Now the next thing that we need to look at is the load carrying capacity of a robot. Okay. Now, after we have decided how many degrees of freedom are required now for a particular task that we want to design a robot for, or we want to buy a robot for, the next thing that we need to do is look at the structure of the robot and the load carrying capacity of the robot. Why the structure of the robot? Because the task has to be inside the work volume, that we know. Okay, so the task has to be inside the work volume. This is a must, of course, for the robot. And different robots have different work volumes. This is something we have seen right again in our second lecture, right at the beginning of the course, that if you're looking at the structure of the robots, if you're having a Cartesian robot which has 3 degrees of freedom, then the shape of the work volume is given like this. Okay. Now, this is a cuboid, and when we are drawing the work volume, there are actually we are dividing this into the position space. So the work volume is divided into position space plus wrist space. What is the meaning of this position space and wrist space? Position space is the wrist point wherever it is moving. You can see in this figure, this robot does not have a gripper, it does not have a wrist with degrees of freedom. So the work volume is corresponding to the position space of the wrist actually. Now the wrist can have additional degrees of freedom, say the roll pitch yaw, which is not shown here. Okay, so in this particular case, we are simply saying that the work volume actually is the position space of the wrist. Okay, we are not considering the wrist degrees of freedom. So in this particular case, it's a Cartesian robot, and each of this has 3 degrees of freedom. It has 3 DOF, and these joints are 3 prismatic joints. Okay, now in terms of load carrying capacity, this type of robot has the highest load carrying capacity. Load carrying capacity, and because of which now you can guess why also. Why? Because this actuation is directly supported. These are linear actuators. So the linear actuator, or this is not a linear, well, maybe a linear actuator, but it's a translating joint. The joint is linear. Okay, so this kind of linear joints, they can support the maximum load compared to rotary joints, and because of which this robot can carry the maximum load. And these robots are, you would see them in industries as gantry robots. They also look like cranes. There are overhead cranes that can actually pick up very heavy load, like they can pick up cars and place them from one place to another place. So in terms of load carrying capacity, this has the highest load carrying capacity. A Cartesian robot has the highest load carrying capacity, and industries, they are used for carrying heavy weights in the form of an overhead crane. So they are mounted on 2 sides, maybe the 2 sides of the wall, and they work like overhead cranes. So this is something important to note, that the work volume is a cuboid, and this robot has the largest load carrying capacity. The second kind of robot we looked at was the cylindrical robot. Okay, this has a hollow cylinder as the work volume. Okay, this also has load carrying capacity, and the load carrying capacity is mainly in this direction. Okay, so it's a vertical load carrying capacity which it has. Okay, now the third kind of robot which we looked at was the spherical robot. Okay, so our spherical robot was something like this, and with a translating joint there. Okay, and this was this part was like this, so it can rotate. Okay, so it can rotate on this. Okay, so this can rotate, and this can go like this, up and down. And this is this has 3 degrees of freedom. This revolute, and prismatic. And what was the shape of the work volume? The shape of the work volume was something like this. Okay, part of a sphere. That was the shape of the work volume. Now these robots are not very good at carrying weight. Why? Because they are supported by revolute joints. Now most robots which have revolute joint robots, they are not very good at carrying weights. So the robots which are made up of translating joints, they have much stronger load carrying capacity. The most common robot is the articulated robot, okay, where we have drawn the work volume like this, which is also spherical. So the work volume is also spherical. Okay, and because of this, the structure of the joint, you can understand that if we have a structure of a joint like this, and it is rotating about this axis, so we have a motor there, right? So we put a motor and rotate it. So if there is a very heavy load in here, what will happen? It will tend to come down because the torque becomes very high on the joint. Whereas for a prismatic joint, where it is moving like this, if there is a very heavy load also, the very high friction on this kind of say rack pinion mechanism which is driving this can sustain such a heavy load. Okay, so articulated robots have large work volumes, but are not very good at carrying load. There has to be some kind of metric by which we should be able to qualify or say that which robot is good in some way and which robot is bad in some way. Okay, and that metric, this is the SCARA robot also exactly which we have discussed in lecture number 2, and the work volume of this is a hollow cylinder. Now the metric by which we discuss about the load carrying capacity is basically called the structural index. Okay, so we define the structural, there is a quantitative measure. So the quantitative is the what we call the which defines the efficiency of design. right? So if you want to say that, is this design more efficient than that one? So we have seen that load carrying capacity is the highest for Cartesian, but is it an efficient design? Now, what do you mean by efficiency in design? So how do you define or how do you measure this? So efficiency in design is measured by these two parameters. The first parameter is the length. Let's call it the total length of robot. Okay, so the total length of the robot is the sum of all its lengths. This is called the length sum, which is also called the length sum. That means the sum of all its length, which is given by sigma I is equal to the first joint to the last joint, and is the sum of AI minus 1 plus di. Okay, so AI is the link length, and di is this link offset, and d is for our prismatic joint, the d is the one that is the variable. Okay, so basically what we are saying is a and d, link length and the offset, are the ones which determine the total length of the robot. Okay, so this is one index, how long the robot is in terms of the length. The second is what is the volume of the work volume. Let's call it work volume. Okay, so this is another parameter. So if a robot has a very long length but it has a very small work volume, then the efficiency design is bad, isn't it? That is quite logical, because we have designed something which is very long. It has taken a lot of material because it's very long, but the work volume is very small. So in that sense, the efficiency is in terms of design is poor. So we define this index called structural. This is called the structural length index, and which is given by QL, which is given by cube root of W. Okay, where L is the total length, this is equal to L, and this is equal to W. Okay, so the ratio of, not 3, it is cube root of W. Okay, so this is an index which actually gives us some kind of an idea of which is a good design and which is a bad design. Okay, because if the length is very long and the work volume is very small, then obviously it's a bad design. Now let's look at an example. So let's look at the Cartesian robot. We said the load carrying capacity of the Cartesian robot is very good. So when we look at the Cartesian robot, let us make the assumption that L1 is equal to L2 is equal to L3 is equal to 1 unit each. Okay, so this is 1 unit each, which means the total length is equal to 3, 1 plus 1 plus 1. What is the volume? It is a cube, so it is 1 cube. So it is cube root of 1, which is equal to 3 now. The index is 3, right? Now if you look at an articulated robot, which is made up of 3 revolute joints. So an articulated robot would look something like this. Is an articulated robot. It has revolute joints. Okay, and if you look at its work volume, it is spherical in nature. And the articulated robot in this particular case, if we say the link length is equal to 1, 1, 1, okay, then we can say that it is, or if the total link length is equal to 1, then it is 1 divided by root 4 pi by 3. Okay. Okay. So what we are seeing in the case of an articulated robot is that it could have a lower index, and in the case of the articulated robot, it is 0.62. Okay. So this basically shows us that in terms of design of a manipulator, the Cartesian robot can carry a lot of weight, which is good in terms of load carrying capacity. But in terms of the design, the manipulator design itself, the index, the structural length index is very small. Okay. Now this is an important parameter which we have to keep in mind, that whether you want to buy one robot for reach or you want to buy a robot for load carrying. So if you want to buy a robot for load carrying, it is a Cartesian robot. If you want to buy a robot which is efficient in design but has a larger work volume, then it's an articulated robot. And this is the reason why most industrial robots are articulated. Okay, because they do not have to carry very heavy loads, but they have to do different tasks. For example, spot welding, spray painting, there is not much load carrying associated, but you require to go into difficult places and you need to have a larger work volume. So industrial robots are essentially articulated robots. Okay, so this gives us an index of trying to compare which robot is better than which one. Now, if you look at the case of the spherical robot, if you just look at the example of spherical robot, then the spherical robot had, let's say it has a length here of L and it has another length here of L, okay, and this is L, and the D axis is here. It can move up and down by that, okay. And what we are seeing is that in the front view it is like this, it's a part of a sphere, okay, and in the top view the robot is it can rotate, so the rotation axis will give a work volume which is like that. This is something we have seen, okay. Now what is the index for this fellow? Okay, so what we can see is that the length is equal to 2L plus D, that's my total length, okay. Now if I say that the robot moves theta1 is equal to 180 degrees and theta2 is 90 degrees, okay, then we can say that just make an assumption that the maximum reach is 60 and the minimum reach is 10, okay. So let us say it is 10 here, okay. So the tool tip has a reach of 60. So let's define it here. So tool tip has a reach of minimum is 10 and max is 10 plus D3, okay. And this much is, so here my D3 will actually come there, okay. That is my D, so yeah, that would be clear. So the tool tip has minimum of 10 and maximum of D3 plus 10, if this is my D3, okay. Now what is the work volume? Work volume is equal to work volume for this robot is pi by 3, 60 cubed minus 60 minus D3 cubed, okay, which is equal to D3 cubed minus 180 D3 squared plus 1080 D3, okay. Now suppose that so 2L was equal to 60, okay. Okay, so this is my work volume. So what is the structural length index? The structural length index is given by 2L plus D3 divided by D cubed minus 180D cubed square plus 10800 D3, okay. So what we are doing here is we are trying to find the structural length index of the spherical robot, and we said that the length of the spherical robot is 2L plus D3, okay. D3 is my prismatic axis and the stroke of the prismatic axis. Now the tool tip is minimum 10 and maximum 10 plus D3, and the work volume is given by 60 plus 60 minus D3 cube, okay. Now 60 is the total reach till here, that is what we are saying, okay. So this is giving us the structural index QL. That's how we find the structural index for a robot. Now apart from the degrees of freedom, the structural index which we have seen, now the third parameter that you need to look at is how well conditioned the workspace is. So how well conditioned or ill conditioned the workspace is. Now this basically means how far you are from a singularity and what is the shape of the velocity ellipsoid. So when we talked about the Jacobian, we talked about the manipulation ability, okay. We had referred to this when we talked about the Jacobian. So manipulation ability we had spoken about when we talked about the Jacobian, and then we said that x dot is equal to j into theta dot, and when we are saying we want to find theta dot, then this is equal to j inverse into x dot, which is equal to adjoint of j divided by determinant of j into x dot, and if determinant of j is equal to 0, then this is a singular configuration. It is singular, okay. Now this is one explanation. The second one is that the manipulation ability is the ability to move in a particular direction, okay. So this j, determinant of j, is, we can define j as an ellipsoid, okay. We can take the singular value decomposition of j and then divide it into three matrices U, sigma, Vt, okay, where sigma is a diagonal matrix which is sigma 1 and sigma n in this way, which determines the major axis and minor axis of the ellipsoid. Now the ellipsoid in space determines the direction of the ease, it determines the ease of motion in a particular direction. Okay. So this is the other point which is very important for us to note, that what are the directions in which the robot can move easily. So if you take a two-link manipulator, so we are having a two-link manipulator like this, and if you look at the work volume of the two-link manipulator, it will be something like this. Okay, so here, here, and here. Okay, so this is my two-link manipulator, and this is my work volume. Well, it's not that big. Okay, so it is something like this. Now, if you look at this two-link manipulator, what we see is that along this axis, if I see, the ellipsoid is something like this, and then the center part it becomes circular, then it becomes like this, and then at the point it becomes singular there. Similarly, in this region, everywhere, it is more or less circular, and then it becomes in this direction with the ellipsoid. Okay, so this is giving me directions in space in which I can move easily, and in directions in which I cannot move easily. Okay, now this is also an indicator of how far you are from a singular position. Okay. So well-conditioned ellipsoids, well-conditioned manipulator is one in which, or well-conditioned manipulator is a manipulator which can move very easily in different directions in space. Okay, so this conditioning, well-conditioned manipulators are those manipulators for which you can move easily in different directions in space inside the work volume. Okay, and they do not become singular somewhere inside. So there is no singularity inside, and you can move easily. Now another parameter is there which is called the inertia ellipsoid. Okay, the inertia ellipsoid is the one that indicates how quickly you can accelerate in a particular direction. The velocity ellipsoid is this one. Okay, so this is giving me the velocity ellipsoid, which I'm getting from taking the singular value decomposition of j and finding the singular values. Now the inertia ellipsoid is the one that gives how quickly you can accelerate in a particular direction in space. Okay, now this obviously depends on this is more a dynamic parameter. So this basically gives is defined as m of theta is equal to j inverse transpose into m theta into j inverse of theta. Okay, so this basically gives us an indicator of how quickly you can move in a particular direction or how quickly you can accelerate, and it depends on the mass matrix. You can see that. Okay, so the previous one was not depending on the mass, it was basically a kinematic parameter, whereas this one is more a dynamic parameter, and this indicates directions in space in which you can accelerate. So these are some of the parameters we saw for looking at directions in space where you can have velocity and directions where you can accelerate very, very quickly. Now in well-conditioned workspaces, there will be no singularity inside, and you would be able to move equally well in all directions. Okay, and in this case, we'll have to examine the manipulator from this direction also. Now, the next thing that we need to look at is the structure of the manipulator. Okay, so what we mean by the structure is solvability. The solvability of the kinematic equations of kinematics. Because we saw in our inverse kinematics that all manipulators need not have inverse kinematic solutions. So if you end up making or designing a manipulator which does not have an inverse kinematic solution, obviously you cannot control it. So that manipulator is of no use. Okay, so your manipulator could be having large degrees of freedom, it could be very well conditioned, but then it may not have an inverse kinematic solution. For example, the human arm. The human arm does not have a closed form inverse kinematic solution. So for that, basically what we need to do is we need to look at the solvability of the kinematics equation, the inverse kinematics equation. Okay, And we have seen from Piper's solution that if the last three axes are intersecting for a 6 degree of freedom, for a 6 DOF system, the last three axes have to intersect. So most industrial manipulators satisfy this condition. So if you look at the last three axes of the Puma robot, we saw the in the case of the Puma arm, we had an axis which was like this, okay, and the roll pitch yaw axis. So this is my roll pitch yaw. Okay, so my last three axes, there was one axis like this, which was the Z4, there's a Z5, and there was a Z6, which was back this side again. Okay, or the last three axis is the roll pitch yaw and the yaw axis, which intersect at that point. So we have a closed form solution as per Piper. Now, is there an exception to this rule? Yes, there is an exception to this rule, and we'll see what that exception is. Now, before that, to satisfy this condition, we see that most wrist mechanisms of manipulators tend to intersect. So this is my 4, 5, and 6. So this is my 4, this is 5, and this is my 6. Okay, so you can see this is my 4th axis. Okay, this is my 5th axis, and that's my 6th axis. So this is a wrist mechanism, also called the intersecting 3-axis intersecting wrist mechanism. So a lot of industrial manipulators satisfy this, because otherwise there will be a problem in the inverse kinematic solution. So we have to keep this in mind when we are designing the wrist of the mechanism. This is another one where we have 4, 5, and 6, where you see that 4, 5, and 6, the axes are intersecting at that point. Okay, basically to satisfy the condition that in existence of inverse kinematic solution, existence of closed form. Numerical solutions are always there, but existence of closed form inverse kinematic solution. So this is something we have to keep in mind when we are designing the wrist. Now, what is the exception to Piper's rule? Now, there is an exception to Piper's rule, and the exception is given here. So this is a manipulator in which the last three axes are not intersecting. You can see that. So there is a gap there. Okay, so there is a gap here. Okay, now this is basically a non-intersecting axis. But the exception to this rule is that this manipulator, although the last three axes are not intersecting, it has a closed form inverse kinematic solution. Now, what is the rule then? Now, what is the exception? The exception is that axis 4, so axis 4 and 2 and 3 have to be parallel. Axis 4 and 2 and 3 have to be parallel. So such manipulators have inverse kinematic solution. So look at your axis 4, axis 3, and axis 2. They are all parallel to each other. And although the last three axes are not intersecting, there is a distance here. Even then, it has an inverse kinematic solution. Okay, so this has an inverse. So this is a solvable system, or IK solution exists. So this is something to keep in mind, that when you're designing the wrist, either we have to make them intersecting, or if you're making them non-intersecting, then what is the exception? Now, in terms of transmission, so this is a robotic manipulator we are seeing. We have looked at degrees of freedom. We have looked at how much singularities are there inside the manipulator workspace. Then now we are looking at the intersection of the wrists. Okay. Now, what about actuation? Okay. Now, actuation of most manipulators are by the motors, electric motors. Okay, so we have motor-based actuation. And what about transmission? So for transmission, basically the motors. Now the motors are heavy because the motors have gears and they have encoders. So the transmission and the motors are placed, okay, at base joints. Most of the motors, heavy motors, go on the base joints. And transmissions can be by gears. They can be via belt, then pulley, then cable. Okay, so let's look at the previous example. So in this particular case, you see that the heaviest motor will probably come on the base. So the heaviest motor is going to come on the base, and it will be mounted on the base somewhere in there. Okay, so this is my motor, which is mounted with a bevel gear onto the first link. So one more motor could be mounted here. So this is for the first joint, which is a rotating joint about this axis. Okay, the second joint is here. So this motor is rotating my second. Now the third motor also could be here only on the other side, and there could be a transmission between this axis and this axis. So there is a transmission between here and here. So there could be a cable drive, or there could be a chain drive, which is transmitting the motion from the second motor. So this is motor 1, motor 2, motor 3. So if you do this way of motor arrangement, what we see is that the load or the weight of the motors are taken off by the base. So most of the heavy motors are put on the base of the robot, and then the motion is transmitted by either by gears, by belts, pulleys, or cables. Okay, this is basically the way the transmission takes place, and each of them has their plus points and minus points. But the fundamental idea and the main concern here is that the motors which weigh very high, are very heavy, they need to be placed near the base to reduce the load, the torque requirement of these motors. Okay. Now, beyond this, we have covered the basic kinematics. What we need for knowing about design, we need to know about the workspace, we need to know the structural index, we need to see how well conditioned the workspace is. We need to look at what we were just talking about, where to place the actuator, where to place the transmission, okay, and then solvability of the system. Now let's look at the gripper design. So what a manipulator does is it has to interact with the world by means of the gripper. Okay, that's how it picks up an object or places an object or interacts with the world. So there are a few gripper designs which are available, and let's look at the gripper designs now. So grippers, which are also called end effectors. So the end effector of a robot could be a gripper. So it can have 2 or more fingers to grasp and manipulate objects, or it could be tools. For example, it is a tool for arc welding, spot welding, spray painting. So end effectors can be classified into grippers, which are fingers, or tools. Now the tool as end effector, you can have arc welding, spot welding, spray painting, drilling, grinding, and then you have grippers, which basically have 2 fingers or are multi-fingered for doing particular tasks. Now in the case of comparison of the human hand and the robot hand, this is a very interesting comparison, that the human, we have 5 fingers, and the robot normally has 2 fingers or 3 fingers. Okay, so this raises the very important question that for grasping and manipulation of an object, how many fingers do you need? Okay, then for force balance of an object for grasping and manipulation, how many fingers are required? So essentially 3 fingers are required with friction at the fingertips. Okay, so minimum for grasping and manipulation, okay, you would be requiring 3 fingers with friction at the fingertip contacts. That means if I have an object and I have a finger like this, robot finger, this is a fingertip contact with friction. So there are 3 forces and 3 moments that can be supported there. Okay, so for this reason, we need 3 fingers are minimum. For the human, there we have 2 major fingers, the index finger, the middle finger, and the thumb finger. The remaining fingers, the small finger and the other finger, is just for support. Now, in terms of sensors, a human fingertip has so many sensors inside. Okay, whereas a robot finger, the poor robot doesn't have sensors. So most of the what a robot cannot do is manipulate objects like humans, because essentially it doesn't have those sensors. Okay. Now, the actuation is also different between a robot hand and a human hand. And in the human hand, there is a lot of redundancy to increase reliability. And there are multiple sensors: force, touch, temperature. Okay, there is a coupled structure for lesser actuators, and the control is simple. Now, this is the human hand, and that's the robot hand, you can see. And there are a lot of joints, there are a lot of differences in terms of redundancy, in terms of actuation, etc. So we will not go into the detail of this, but we'll basically look at a few robotic grippers. So robotic industrial grippers. Okay. Now the first thing that we need to know is the actuation. They can be actuated by, for example, a 4-bar mechanism. They could be actuated by gear and rack. There could be a cam actuation, screw actuation, rope and pulley actuation. Other types can be magnetic, vacuum, adhesive. So this is a focus on industrial grippers only. and industrial grippers are normally of these types. Now, something interesting to note here is that the force applied on the object should be normal to the object. For example, if I have an object here, and if I apply a force in this direction, what will happen is there will be a resultant in that direction, because of which the object will end up moving in that direction. Okay, so this is a bad gripper design. So if you're designing a gripper, you need to remember that the force that is applied onto the object has to be normal to the object. Okay, and this is showing a normal object. This is showing the normal, the force which is normal to the surface of the object. Okay, in order to grasp it successfully. For that, we can use a mechanism which is like this, or a mechanism which is like this. Okay, so this is for opening it, and this is for closing it. So when it is moved in this direction, it is opened, and when it is moved in the reverse direction, it is closed. But something to note here very carefully is that the design of the mechanism. This is a cam actuated mechanism. The previous one was a linkage actuated mechanism. This is a cam actuated mechanism where we have a cam here, and there is a spring which opposes the closing. So essentially, you move the cam forward or you move it backward, and that is going to open and close the gripper. Again, the force that is applied is normal to the surface. So if I have the object here, the force is going to be normal there. Now, it is very easy to compute. If you're designing a gripper, you need to compute what is the force acting on the fingertip, and it's very easy to compute simply by looking at the free body diagram and then finding the reactions in each of the linkages. So this is a linkage mechanism, and if I'm going to apply a force Fg there, suppose the force Fg is 25 newtons, then what should be the Fa? What should be the force applied by Fa, either by piston cylinder mechanism or by a linear actuator? And basically, I just break it up into the free body diagram, look at all the forces acting at all the joints, and then by looking at the equilibrium equations, that is sigma F is equal to 0 and sigma M is equal to 0, I can find what Fa should be equal to. So in this particular case, we find Fa is equal to 74 pounds. Okay. Now to calculate the forces, okay, this is another case of a different gripper where we have different linkages, and we can very easily compute what are the forces that are required. This is another gripper which is actuated by a screw mechanism. So we can have a motor here which is rotating, and when it rotates, this this gripper closes or opens. Okay. Now this is so far what we have seen are basically grippers. Grippers, as the name indicates, is basically for gripping objects. Okay. Now there can be other applications where you cannot grip properly. So gripping is using 2 or 3 fingers. Okay. But there can be applications where it is difficult to grip, and a 2-finger gripper will not solve the problem. For example, when you're handling soft material, okay, soft material like cloth. Okay, so when we're handling cloth, okay, a gripper will find it very difficult to handle. Other things which are difficult to handle is say sheet metal, then wood, okay, then other things like bottles. These are difficult to handle by either 2-finger gripper or multi-finger gripper. So if you're trying to pack bottles or cold drink bottles like Coke bottle, what is required is that it should be able to pack as many bottles in one crate as it can do in one shot. So if you're using a 2-finger gripper, it catches one bottle, then puts it there, takes one more bottle, puts it there. That will take a lot of time. Whereas if you can have a gripper which is going to take maybe 24 bottles in one shot and put it, then that is better. Okay. So these are some of the examples where 2-finger grippers would find it very difficult to do. Soft materials, cloth handling. Handling cloth is very difficult. Handling paper, cloth, paper is difficult. Then sheet metal and wood. Okay, handling wood is again difficult. Sheet metal has a lot of applications in industry. In automobile industry, you have to use a lot of sheet metal. Now, how would you handle that? 2-finger grippers can't handle that. Handling bottles, handling light bulbs. These are all difficult tasks for 2-finger grippers. Now, what is done for that is for handling metallic parts, metallic sheets or steel plates, we can use a magnetic gripper. Now, how this magnetic gripper acts is shown here very clearly where we have the steel plate and we have a permanent magnet which is shown here. Okay, so the permanent magnet base gripper is fitted onto the robot arm which is shown here. It is fixed onto the wrist. So what is done is this gripper is taken and is placed on top of the steel plate, and this permanent magnet will go and get attached to the steel plate. Then the gripper lifts the plate and takes it to wherever it is required, and then there are pushers. Air cylinder actuation is there. You can look at these are cylinders for actuation. So these air cylinders are actuated and these pistons come out and push this plate down. Okay, so wherever it has to place it, it will place it there and then push the plate out of the permanent magnet gripper. We could also have electromagnet here. So in the case of an electromagnet, after the electromagnet is placed onto the sheet, it is energized. And once you want to release it, you just de-energize the magnet and it will release the sheet. Okay, this is very commonly used in industrial applications for lifting steel plates. Now, advantages of magnetic grippers is that they are very fast. They work very fast to magnetize and demagnetize. There is no problem in variations in part size. For example, large sheet and a smaller sheet. Okay, they can handle metal parts with holes and non-uniform surfaces. Then they require only one surface for gripping. Unlike a gripper which catches in two surfaces, this catches only in one surface. Now, the other kind of gripper which is used very commonly is the vacuum cup gripper. And how it works basically is we have a vacuum cup which is shown here. So it is taken and pressed onto the object and the air is expelled. Once the air is expelled, what happens? The vacuum is created and this gets attached onto the gripper. And then you take it wherever you want and then release the vacuum. This is an example of a vacuum cup gripper. Now this, as you can see, can lift very simple things like wood. It can lift glass. For example, in the automobile windshield, when the robot actually assembles the windshield, so it picks up the windshield by using this magnetic grippers. Okay, so wood is another example. Wooden planks which can be very easily picked up by magnetic grippers. Sorry, not magnetic grippers, but this kind of vacuum cup grippers. Magnetic grippers is only for steel and ferromagnetic material. Now, this is also used extensively for packing. Okay, so many applications of magnetic grippers. So canning, tray marking, bottling, box marking, capping, labeling. Okay, so all this kind of industries, auto manufacturing, steel, conveyors, disc, electronics, heavy industry, they use magnetic grippers. And the advantage of the magnetic gripper is that a lot of the magnetic cups can be placed in one shot on the wrist. And in one shot, you can pick up many bottles and then you can pack it. This is an example showing a vacuum cup gripper lifting wooden board. So there are 4 of these wooden cups and it is taken and pressed onto the wooden surface and then it is picked up. Vacuum is created and then is picked up and placed somewhere else. Parallel jaw grippers are again industrial grippers where the opening and the closing of the 2 fingers is done by a rack pinion mechanism, as you can see here. So when this rotates, what will happen? The fingers will come together or the fingers will come away. And that is basically how industrial grippers work. Now, simple pneumatic grippers are shown here where it is trying to catch a ball, where you should not apply too much weight, too much force, and just to catch the object. There are other applications, for example, a roller type gripper for holding. These are special purpose grippers. For example, when it is catching a ball, it should be able to roll the ball inside and then constrain it. That's the function of this gripper. Intake roller grippers. Okay, so this is also a gripper which is constraining this ball. So it will let this ball come in and then it will constrain it. Okay, so this is a pulley mechanism for lifting, then a sliding section mechanism for lifting again. So the object is kept inside here, it is held and then it is picked up. Okay, so these are some of the examples of that we need to keep in mind when we are designing a robotic system, because we start off with degrees of freedom, then we see other parameters that are required like structural index, then we see whether it is well conditioned, then we went on and saw whether the inverse kinematic solution is possible in terms of the risk design. Okay, and then finally to make or to apply the robot in an application, we need to see what is the kind of gripper that we are going to put on it. And today we looked at different grippers, right from industrial grippers to magnetic grippers to vacuum grippers. and special purpose grippers like the ones that is shown here for catching soft toys and soft ball for different applications. So there are special purpose grippers which are based only for catching particular kind of materials, and the actuation of such grippers can be by means of 4-bar linkages and mechanisms. So there is a 4-bar mechanism, lifting mechanism, okay, which can be fitted onto the end of a robotic arm. So today we'll be stopping here, and in the next class we'll move on to looking at applications, industrial applications where robots are used. For example, whatever we have studied so far is making the very basic assumption that the robot can be used anywhere, but it is not so. In industries, there are very specific industries where robot can be used. Robots cannot be used everywhere, and if you try and use robots everywhere, then what will happen is we'll end up with failure in terms of economics is not viable for using robots everywhere. So today we'll stop here, and in the next class we'll look at industrial applications, mainly where robots can be used, where robots may not be used, okay, and then we'll look at a few applications of spot welding, spray painting, and safety. So how robotics is different from other mechanical machinery like NC machine and CNC machines is that the safety aspect of robotics is very, very important. So when we are talking about robotics, safety is the one that has to be, there are guidelines for safety which have to be followed, and that is something that adds to the cost of applying a robot or using a robot in industry. And on similar lines, what is the future direction of industrial robotics? Okay, so that is something we'll be looking at in the next class. So we'll stop here. Thank you.